If you draw a closed circuit of atomic steps in a perfect crystal, and then draw that exact same sequence around a structural defect, the loop fails to close. That directed closure failure is conventionally defined as the Burgers vector. This atomistic framing is highly effective for pedagogy. It provides a diagrammatic way to introduce basic plasticity and visualize how local atomic order survives even when the broader lattice is flawed. Yet treating the Burgers vector strictly as a geometric descriptor of a broken atomic plane is mathematically incomplete. It traps a dynamic, multi-scale property inside a static picture. In rigorous mechanics, the Burgers vector is an exact translational obstruction to integrability. Integrability, in this context, means that a locally defined lattice frame cannot be smoothly expanded into a single, continuous global structure. The vector measures precisely where, and by how much, that local-to-global integration fails. The same object appears as a lattice translation in crystallography, a homotopy class in topology, and a measure-valued flux in continuum mechanics. Because it consistently measures a translational obstruction, the vector remains the conserved link between atomic scale periodicity and the incompatibility of the continuum. Restricting this concept to a simple diagram prevents the accurate modeling of macroscopic plastic flow. To simulate complex, evolving material systems, the vector must be tracked as it shifts from a discrete atomic count into continuous mathematics. We begin this mathematical shift by moving past individual atomic steps and analyzing the crystal as a continuous medium, described entirely by an elastic distortion field. In this continuum space, the Burgers vector is the period of an incompatible distortion field along a closed circuit. Using Stokes's theorem, we convert that integral into a two-dimensional flux. The boundary loop becomes a bounded surface, computing the net defect charge piercing that plane. This mathematical conversion is represented by the dislocation density tensor, introduced by John Nye. The Nye tensor takes a localized line density of parallel defects and translates it into a macroscopic spatial measure of crystalline incompatibility. Within this tensor equation, the Burgers vector acts as the invariant coefficient. It multiplies the continuous line density and the tangent direction, locking the discrete physical charge into the smooth field equations. This allows physicists to replace an isolated Volterra line, which produces infinite stresses at an infinitely sharp point, with a smoothed, regularized continuous core. By treating the defect this way, the Nye tensor formulation successfully decouples the conserved translational charge from the highly non-uniform singular strain at the exact center of the atomic core. But the Nye tensor relies on a small strain approximation. To model severe deformation, especially when structural rotations are involved, the continuum field model must be mapped onto non-Riemannian differential geometry. We establish a material connection, a local coordinate set, or coframe, that precisely tracks the physical lattice directions as they twist and bend through space. Cartan's first structure equation measures this space. This equation allows us to construct an infinitesimal material parallelogram and calculate whether its boundaries mathematically close. When the affine development fails to return to the origin, the resulting geometric gap is known as translational holonomy. Under this framework, the Burgers vector is exactly that holonomy. The explicit geometric measure of this translational mismatch is called the material torsion two-form. This isolates specific defect types. In a crystalline material, pure dislocations generate torsion, while rotational defects, known as disclinations, generate material curvature. If a system contains only dislocations, you can simply add their translation vectors together. But when rotational disclinations are introduced, the translational holonomy becomes highly sensitive to your frame of reference and your starting base point. The full defect charge can no longer be treated as a free translation vector. It must be calculated as a combined element of the Euclidean group, coupling rotation and translation together. Standard vector addition is a specialized local approximation. In a coupled dislocation-disclination system, it fails entirely. Global accuracy requires calculating the full affine holonomy. Defining the vector as a geometric gap naturally leads to the topological classification of ordered media. Topology strips away the physical energetics of the defect and redefines the Burgers vector strictly as a topological charge, corresponding to free homotopy classes of loops within the crystal's order parameter space. This imposes a rigid structural constraint. An isolated dislocation line cannot terminate freely in the middle of a perfect bulk crystal. The topological charge has nowhere to dissipate. To analyze networks where millions of these constrained lines intersect, researchers rely on geometric measure theory. In this mathematical framework, isolated dislocation lines are represented as de Rham currents. Each current carries a specific coefficient drawn directly from the crystal's lattice group. When these currents intersect at a node, we apply the boundary operator from differential topology. The mathematical identity states that the boundary of a boundary is exactly 0. This requires that the sum of the incoming and outgoing vector coefficients at any intersection must perfectly cancel, enforcing what metallurgists call Frank's rule for vector conservation. Frank's rule for vector conservation is the physical manifestation of this identity. In the language of measure theory, a boundary cannot have its own unconstrained boundary. Therefore, the total vector charge entering a node must equal the charge leaving it. Bridging these topological rules with physical materials brings us to the practical frontier of solid mechanics, the experimental measurement of bulk crystals. This creates an inverse problem. Laboratory instruments measure continuous elastic strain and lattice rotation, but predictive engineering requires the exact discrete topological charge. Modern methodologies like 4D scanning transmission electron microscopy and dark field X-ray microscopy attempt to isolate this charge by mapping the crystal's response to electron or photon scattering. This image shows a luminous symmetric grid of diffraction spots generated by empirical reciprocal space data. By analyzing specific diffraction vectors, microscopists test contrast conditions to isolate and classify individual defect properties. However, deducing a specific discrete Burgers vector from a continuous bulk distortion measurement is mathematically underdetermined. Multiple discrete line configurations can produce the exact same continuous field. Computational algorithms require strict physical priors to solve this. By assuming parameters like minimum line energy, network sparsity, or non-negativity, the models filter out statistically stored dislocations that mask the net vector flux. Modern materials microscopy does not directly photograph a defect's charge. It captures the highly specific boundary data necessary to mathematically invert the continuous distortion field and algorithmically reconstruct the discrete invariant. From a discrete translation in a lattice, to a continuous tensor flux, to a topological current, and finally into inverse boundary data. Across all of these scales, the vector retains its mechanical utility. It acts as the exact bridge coefficient used to calculate the peach color forces and the elastic energy kernels that govern material strength. This is why maintaining precise vector quantization during the mathematical transition from discrete variables to continuous limits is strictly required. Any failure to conserve this charge reveals a critical modeling error in the simulation rather than a valid physical mechanism. The Burgers vector acts as the absolute compatibility condition. It is the common invariant that allows an atomistic core, a continuous field, and a diffraction signature to be compared as descriptions of the same physical defect content.